Problem number 21. F of x, y, z is a square root of x squared plus y squared plus z squared. We want to integrate this function over the region with y is less than or equal to 0. X squared plus y squared plus z squared is less than or equal to 4, and z is less than or equal to -1. We want to do this using spherical coordinates. Why do spherical coordinates make sense here? Well, one is that the integrand is just rho in spherical coordinates. That's really nice. This right here, this is showing that rho squared is less than or equal to 4, or rho is less than or equal to 2 here. Y is less than or equal to 0. The projection of this into the xy plane is going to be, okay, so let's see, y is negative here, so we're shading this part here. So what does this tell us about theta? Theta is running, so 0 to pi. It starts at pi and goes until we hit 2 pi. Okay. Let's see. So far we've got, ultimately we're looking for bounds on theta and rho and phi. Right now we have bounds on theta. We have an upper bound on rho here. Now we need to start thinking about the z is less than or equal to -1 bound. Okay. Let me draw a picture here. So x squared plus y squared plus z squared is less than or equal to 4. That is a sphere of radius 2. And then somehow we are cutting this off. So I should say that this intersects down there at z is equal to -2. Somehow we're cutting this off here at z is equal to -1. So we are integrating over that. It's a spherical cap on the bottom of the globe. Spherical cap on the bottom of the sphere. In cross section, if we were to look at this, aiming on in the from the positive y-axis, so projecting this to the yz plane, what this would look like would be something like this. Okay, so what information does this tell us? Well, this is hinting towards information concerning phi. So first off, we can see here that the biggest phi can be, so remember phi is the angle you are from the positive z-axis. This is phi is 0. This phi is pi over 2. This is phi is pi. The biggest phi can be is pi. And the smallest phi can be corresponds to this angle right here. What is this angle? Well, this is corresponding to, this point right here has z is equal to 1 and z is equal to -1 and rho is equal to 2. But we know that z is equal to rho cosine phi. -1 is equal to 2 cosine phi at this angle here. Cosine phi is -1/2. This occurs. This occurs when phi is going to be, let's see here. This is going to occur when phi is equal to pi over 3. Sorry, not pi over 3, 2 pi over 3. Pi over 3 would be cosine phi is 1/2. But, if z is positive, but this is, phi is from 2 pi over 3 to pi. Okay, so we've got bounds here on theta and phi. We have an upper bound here on rho. The biggest rho can be here is 2. Well, what's the smallest rho can be? So the smallest rho can be is going to be corresponding to this line right here, z is equal to -1, but z being rho cosine phi is equal to -1. Rho is equal to -1 over cosine phi. So rho has to be at least -1 over cosine phi. Rho can be from -1 over cosine phi to 2. Now, important point here, you might say to yourself, hey, I thought rho always has to be greater than or equal to 0, and it looks like we're having rho being, rho could be something negative down here. But remember, if phi is between 2 pi over 3 and pi, we're down here, cosine phi is negative, so this expression over here, negative over negative, is positive. Okay, so our bounds on our integral are going to be, let's see here, theta runs from pi to 2 pi, phi runs from 2 pi over 3 to pi, and then rho runs from -1 over cosine phi to 2. Okay, and then we are integrating, the integrand is rho times rho squared sine phi d rho d phi d theta. So that always comes in, that's the Jacobian here, and then that's the particular integrand. This should be, in the interest of time, I'm not going to evaluate this, but you should be able to evaluate this integral.